The natural base E. First are your state standards. Below that is your success criteria. Explain the natural base E. Simplify natural base expressions, graph natural base functions, and solve real-world problems using exponential growth and decay. You have one vocabulary word. It's very important. So we have a graph and a table, and it's part of your key idea here. So your natural base E. So the history of mathematics is marked by the discovery of special numbers such as pi and I. Another special number is denoted by the letter E. The number is called the natural base E. The expression 1 plus 1 over x, all raised to the x power, approaches E as x increases, as shown in the graph and table. All right, so you have the table of values here. You can see here's the graph where it approaches this line. So E is this dashed red line. You can see as x gets larger, this line approaches that line. So the natural base E is an irrational number. That makes it similar to pi in that it's irrational. It is defined as follows. As x approaches infinity, you can see here x is going towards positive infinity. 1 plus 1 over x raised to the x power approaches E, or this dashed red line. This is something else we'll look at. Continuously compounded interest. When interest is compounded continuously, the amount A in an account after T years is given by the formula A equals PERT. So P times E raised to the RT power. P is your principal, R is your annual interest rate. E is going to be this number here, this 2.71, this irrational number, but that number there, and then T. So E is actually in your calculator and it knows this value. Example 1, simplify natural base E expressions. Simplify each expression. All right, so A part says e to the third times e to the sixth. So this properties of exponents. You keep your base and add your exponents. So A part's going to be e to the ninth power. B part says 16e to the fifth divided by 4e to the fourth. So you can divide the numbers. 16 divided by 4 is 4. Same base. When you're dividing, when you have a quotient, you subtract exponents from top to bottom. So 5 minus 4 is 1. So 4e, or 4e to the first power. C part says 3 times e raised to the negative 4x power, all squared. So since the negative 4x is only attached to the e here, we're going to evaluate everything to the second power. So 3 squared is 9. And then e raised to a power to another power, a power to a power, remember you multiply your exponents. So keep the base, multiply exponents. So e, we are going to divide, but let's add one more step here. E to the negative 8x. And then if we want to simplify that, we have to get rid of negative exponents. So we move this to the denominator and make it positive. So e to the 8x. And this would be considered simplified. D part says the square root of 4 e to the 2x power. So remember the square root is equivalent to something to the 1/2 power. So we can raise all of this to the 1/2 power. So the square root of 4 is just 2. And then we've got e to the 2x to the 1/2 power. So we already took the square root of 4. So we already did 4 to the 1/2 power, which is 2. And then we have 2x to the 1/2 power. So half of 2 is 1. So we're going to have 2e to the x power. Example 2, graphing natural base functions. Determine whether each function represents exponential growth or exponential decay. Then graph the function. All right, so your key idea here, this is very important. A function of the form y equals a times e raised to the rx power is called a natural base exponential function. When a is greater than 0 and r is greater than 0, the function is exponential growth. So here you can see a is assumed to be 1 and r is positive. So this is exponential growth. When a is greater than 0 and r is less than 0, the function is exponential decay. So here we've got these two basic functions, y equals e to the x, that's exponential growth, and y equals e to the negative x, which is exponential decay. All right, so when we look at a part, a is 3, r is 1, greater than 0, so it's positive. So a part is exponential growth. B part says f of x equals e raised to the negative 0.5x. So r is less than 0, so it's exponential decay. All right, so it says determine whether each function represents exponential growth or exponential decay, then graph the function. All right, as always, you can make a table of values, pick your x's and plug it in to find your y values to graph, but I want you to see how to do this using your calculator. So make sure you know where the E button is on your calculator. So if you go to y equals to graph, we're going to graph 3e to the x power. So we're going to do 3. Now e is right here below pi, and you can see it's in blue, so you have to do second divide to get the e button, and then you're going to raise it to the x power. All right, so 3e to the x power, and then we hit graph. And you can see that is exponential growth. And again, if you wanted to see the table of values to sketch a graph on your own, just do second table, and you could go through and find some points to sketch that graph. All right, so let's graph B part the same way. So there's no a value, so it's assumed to be 1. So we can just do second plus so we go second divide, which gives us our E button, and then we're going to raise that. I'm going to put this in parentheses to make sure it gets all of it here. So negative 0.5x in parentheses. So I've got e raised to the negative 0.5x power, hit graph, and this is going to be an exponential decay function. Example 3, modeling real life. You and your friend each have accounts that earn annual interest compounded continuously. The balance A in dollars of your account after T years can be modeled by A equals 4,500 E raised to the 0.04 T power. The graph shows, here's the graph here on the side. The graph shows the balance of your friend's account over time. Which account has the greater principal? Which has a greater balance after 10 years? All right, so your account shows that you have a starting amount, or your principal is $4,500. So you have a starting amount of $4,500. You can look at the graph and see your friend's balance started at $4,000. So you have a greater beginning balance. All right, so which account has a greater principal? That would be you. And which has a greater balance after 10 years? All right, so for your account, we can plug in 10. So account equals 4,500, E 0.04, and we want to know for 10 years. And again, we can use our calculator to do this. So I'm going to do $4,500 times E. And then I want to raise that. I'm going to put this in parentheses just to make sure it raises all of it to the power. Remember, your calculator only does what is inputted, and it's programmed to do certain things. So I try to make sure that it knows exactly what to do. And then hit enter. And that's going to give you 6713.21 approximately. So your account is going to be 6713.21. All right, so this is you. And then your friend, we can look at the graph, and the principal we already established is 4,000. And here the principal is 4,500. So you have the higher principal. But if we look at after 10 years, we're going to use the graph to see what your friend has after 10 years. So you can see these go 4, 6, 8, 10, 12. So 10 would be right here. And you go up here. And so this is 6, 7, 8. So this is going to be about $7,200. So it says which account has the greater principal and which has the greater balance after 10 years. You have the greater principal starting out, but your friend has the greater balance. You're going to have a balance of roughly $6,700, and they're going to have about $7,200 after 10 years. Okay, so that's everything on the natural base E. If you have any questions, please let me know.